Hey everyone, welcome back to the channel, and in today's video I'm going to tell you a really interesting story, a story of an innovation that was meant for developers but it ultimately shaped the way we design interfaces today. But before we start the video, I'm going to tell you about the workshop that I'm hosting on coming Saturday and Sunday on building career as a freelance designer. So I've been doing freelancing on the side for last four and a half years, and in the last 1.5 years alone I've worked with more than 60 startups and clients on projects ranging from UX design to UX consulting. So if you're someone who is struggling to get their careers up and running as a freelancer, then this session is for you. The registration link will be in the description. You can check out the details, and as a bonus, all the attendees of the session will get all the source files, all the presentation copy, as well as a free portfolio evaluation. So hurry up, I have only limited seats for this, and let's get started to our video. So let's start the video with a really simple question. Can you find a connection between these two statements? First, how will you make sure that your design looks good on every device out there on planet Earth? And the second is, why artboard sizes on Figma, XD or Sketch is different than the actual resolution of the devices. Now, I want you to pause this video and answer these three questions. The two statements as well as the top question in the comments below. And what do you think the reason is, right? If you don't know this, then don't worry. I'm going to explain this in the end of the video, but stay tuned for that. But if you know the answers, you can just comment it below and let's see how many of you get it right. Okay. So the story begins with the launch of the first true smartphone. Now, the first iPhone, that's what I'm talking about. And it was launched by Steve Jobs on 29th June 2007. Now, I said true smartphone for a reason, because before this, the phone used to have like really small screen and a physical keyboard, whereas the first iPhone was the first all touch screen device with no physical keyboard, and it gave birth to the existence of full screen apps as well as an app store, and the rest is in history. Soon after this, the first commercially available smartphone that was running Android was HTC Dream, also known as T-Mobile G1, and it was announced on September 23, 2008. Both these Android and iOS devices were groundbreaking at the time. But soon after the launch, both Apple and Google realized there's a problem, and it was a crucial one. It was not there that time, but it was about to come. And the problem was, how to design for the millions of devices that are out there and the gazillions of devices that are going to come in the future. Now, the problem was not that severe for Apple at that moment, because there were only few models of iPhone in circulation, so it's okay to design only for those screens. But it was way more severe for Google's Android, because Android was supposed to run on devices manufactured by other companies, and it's only recently when Google has started building their own Pixel lineup. But even then, Android was supposed to be loaned to other manufacturers, and they can run it on their own devices like Xiaomi, OnePlus, etc. Anything that is not running iOS is basically running an Android, right? So this was the problem. Now, this statement is actually an uber problem. It stems from two main problems that is related to how devices are manufactured. So let's have a look. The first thing is called screen resolution. Now, I have put up an example here. On the left you have a smartphone, and on the right you have a full HD TV. Both of them have the exact same resolution, 1920 by 1080 pixels. But if you see, both of them has a really different physical size and form factor. So if you design something using just the absolute value of pixels, it's not gonna scale on every device, because pixel resolution clearly ignores the notion of physical size. You won't be able to understand what device it's running on. So pixel value or the resolution value is actually not a good metric to design or scale anything. The next thing is called screen densities, and it's usually measured in terms of PPI or pixels per inch. And as the name suggests, pixels per inch means the number of pixels on a 1 by 1 inch square of the screen. So here I have two examples to demonstrate the effect of PPI. So on the left you have a 4 PPI screen, and on the right we have a 16 PPI screen. Now 4 PPI means that we have 4 pixels in 1 inch square area of the screen, whereas on the right we have 16 pixels on 1 inch square area of the screen. Now it's immediately apparent that higher PPI means lower the pixel size. So if you see here on the left, 1 pixel is this big, okay? And on the right, 1 pixel is this big. correct? And if you see, there's a massive difference between the two. Now let's say you're designing a UI and that UI element is 4 by 4 in size. So it's gonna look this big on the left screen, which is the lower PPI screen, as well as if you see that same 4 pixel UI is gonna look this small on the higher PPI screen. So it's gonna look really different based on the PPI of the screen if you're designing in absolute pixels. And typically the higher end smartphones have really high PPI, whereas the budget smartphones usually have a lower PPI. So designing in absolute pixels is again a problem. So both Apple and Google knew that they have to design something that is independent of these two values. They have to design something that is relative in term, can be fairly easily used, and is scalable as well. So a new term, a new metric was designed. It's known as density independent pixels, DP or DIP in short. A density independent pixels allow designers to create an asset that appears in an expected way no matter density or resolution of the target device it's running on. It actually depicts the physical size of the screen. So in this example you're seeing here, if I let's say design a button theoretically and it has some dimension in DP, then it's going to look the same size on both the phone as well as on the tablet. So that's the underlying idea of DP, density independent pixels. Now let's quickly see how density independent pixels are calculated. So 1 pixel by 1 dp is equal to the PPI of the screen that you're designing for divided by 160 PPI, which is also known as baseline density, and it's a constant. So 160 PPI used to be the average densities when this metric was designed, and that's why it's kept as a constant. On the top you have to replace this number with the PPI of the screen that you're designing for, and it will give you different scaling factors. So if your phone has 160 PPI, in that case 1 pixel becomes equal to 1 dp, and that scaling factor is known as 1x. Now let's see another example. If the phone's PPI is 320, in that case 1 dp is equal to 2 pixels, and that scaling factor is known as 2x. Now I can keep on replacing the top numbers with different multiples of 160. For example, if you add 480, in that case 1 dp will be equal to 3 pixels, and that is known as a 3x scaling system. So you can define 1x, 2x, 3x, 4x, 5x scaling factors. Okay, and this is a term that is exactly used the same way in Android development as well. Now let's see why DP is an immensely powerful metric. So here I have two devices. On the left you have a phone with 800 by 1280 pixel screen resolution. On the right you have a tablet with 1280 800 pixel resolution as well. So both of them has the same resolution. On the right the tablet is actually at a 1x density, and on the left the phone is at a 2x density, 320 ppi. Now the question is, since the resolution is same, should you be designing same screens for both? Now just by seeing this two metrics you won't be able to understand what to do. If I don't design that box around it, you will never know which one is what, right? You'll never know which one is a phone, which one is a tablet. So how would you design about it? Now let's change these two DP terms and let's see from the lens of a DP world how this will look like. So if I convert these to DP, since the right tablet is at baseline density, 1 pixel is equal to 1 dp, so the DP resolution comes out to be 1280 into 800 dp. Whereas the left one, the phone was at 2x scaling system, which means 1 pixel is equal to 1 dp is equal to 2 pixels, and that gives us 400 by 640 dp resolution of the phone. Now by looking at just this one metric, you can quickly understand that the right side screen is larger than the left side screen, and that's how it's giving us the sense of physical size of the device. Now let's quickly look at another example. Here you have two phones, both of them. So first phone has like the resolution of 800 by 1280 pixels, and the right phone has a resolution of 400 by 640 pixels, and both of them are at different PPIs. So this is at 1x and this is at 2x. Now the question is, should you be designing different screen for this scenario? We have two different resolutions as well as two different PPIs. Now pause this video and write your answers below. Let's quickly see how it is. So if we change then into the DP terms, you would see that both of them turns out to be 400 by 640, 400 by 640 dp, which means these two are exactly same size. So you don't have to design two different screens, your same screen will scale in both the scenarios. So now if you see, the immense powerfulness of the entire system is that just by one term, just by this one dp term, you're able to figure out if these two devices are same size or not physically. And that's the whole power of the dp system. Let's talk about density buckets. So manufacturers don't usually adhere to the same standard of PPI as shown here. They never create screens at 160, 320, 480, exact these PPI numbers, because it's a physical process and a physical manufacturing process, and these numbers tend to have in a range. So they never design it exactly the same values. So to address this problem, Android system designed something called as density buckets. So with density buckets, what it means is that, let's say if your phone's actual PPI, actual density is, let's say 174, then it will be mapped to this first bucket. So 160 till 240 is one bucket, then 240 till 320 is another bucket, 320 to 480 another, 480 onwards in another bucket. So if your resolution falls in between different bands, it will be mapped to one of these PPI, so that you can create that DP conversion easily. They have also been given a friendly name, because remembering these numeric terms is different. To make things more easy and collaborative, the friendly name was given in the right. So for example, 160 PPI or the 1x scaling system is also known as MDPI. Now the DPI here does not mean density independent pixel, it means dots per inch. It's another name for PPI. Okay, so don't get confused with DPI with DIP or DP. This DPI means dots per inch, which is equal to, which is actually another term for pixels per inch. Okay, and if you have, let's say 240 PPI, then it's also known as HDPI or 1.5x scaling factor. So these are just the multiples of 160 if you're seeing here. And then you have XHDPI and double XHDPI and so on. So you keep on increasing the x's in front, and you keep on getting the different sizes. Now phones come at that particular time, the phones used to come at least max of 3x, but now in 2021 the phones comes at 4x and 5x resolutions as well. So I've explained you how DP is calculated, how it works, how logical density buckets are calculated, and how they work. Now let's quickly understand how this all concept work in a real app scenario. So what happens is, every app contains 1x version of their screens, so they are designed at 1x versions. Now as soon as you install this app on an Android system or a system that is running Android, the first question that the app asks the Android system is, what kind of density are you running on? And to which the Android system replies to the app that, hey, I am running on, let's say XHDPI. To which the Netflix app says, hey, I know XHDPI means 2x. So what it does, it scales the 1x version of the screens to 2x and delivers that 2x version to the Android system, and then the Android system displays that app on your screen in 2x scaled format, because it knows it's a 2x screen. Similarly, if the, let's say, Android system says it's a 3x screen, then the app scales that version to 3x, and then the Android system displays it on your screen. So that's how it always make sure that the UI looks perfect no matter what kind of screen it is or PPI it is, because it's now scaling everything into the set resolution, into the set density bucket, and then serving it to you on the phone. Now this works really well for everything except the graphics or the images, because everything else is vector. So even if you scale the vector up or down, it will not lose its sharpness or clarity. But it works a little bit differently for images and graphics. Now let's see how it works for graphics and images. So the app still contains all the UI at 1x scale, but now it also contains all the graphics and images in different scaling factors. So for example, you have image 1. The image 1 will be available in the app in different formats. It will be available at 1x, 2x, 3x, 4x and 5x, whatever, right? So now the entire app bundle consists of these two things: a scaled version, the 1x version of the UI, as well as images at these different resolutions. Now as soon as the Android system tells the UI, tells the app that, hey, I'm running on, let's say, a 2x density screen, what happens is the app scales the UI into 2x, here and picks the 2x version of the asset, bundles them together, and then send it to the Android system, right? And by doing this, it's a very ingenious way. What happens is you're sending out the most optimum resolution to the Android system to display it on your phone. Now, for example, different phones are devised by different manufacturers. Some are budget smartphones, some are high-end smartphones. So let's say showing a 4x, a really high version of the UI, to a very low-end phone will not make any justice to it, because it cannot show you that crispness and sharpness. So what it does, it picks the appropriate scaling factor to scale the UI, and it also picks the appropriate image asset along with it to show and display it on your screen. So that's how it works with both DP scaling as well as image assets. And the 1x, 2x, 3x version of the assets that you actually create, and this option is available on Figma, XD Everywhere. On the export side, you'll see 1x, 2x, 3x drop down. This is exactly what developers ask from designers, that hey, when you're adding some graphics to it, just send me these version of the graphics as well. And when you mark anything in the export on those 1, 2x, 3x option on Figma and XD, when they try to inspect it, they will get all these values automatically from your graphic and icons or image assets that you're using. So that's how it works with the entire DP system as well as the image ecosystem. So now the question comes to, how did this all DP and this image conversions and these density buckets help designers? So the idea was actually a solution for developers and was implemented in Swift for iOS and Android Studio for Android to record respective apps on the platform, and it was there to help them design these apps more scalably. But since devs and designers have to collaborate on designs all the time, all the design softwares that were there at that time, like Sketch, Photoshop, and later Figma and XD as well, adopted the same workflow to make things easier for collaboration. So it's like a mirrored workflow for designers. We do exactly what devs do, but visually. So devs also works on 1x system. They also add these scaling factors. They also use images and these different things. And the design software that we use has also adopted the same thing, so that there's no misunderstanding that you need to do. Earlier, it used to be really difficult to do all this. But since coming from this 1x scaling system, we have simplified a lot of miscommunication and have removed all this miscommunication actually. So that's how it helped the designers. And coming back to our first question, how will we make sure that design looks good on every device? So the answer to it is that we'll design everything in 1x system and in DPs, so that the OS can automatically scale it to the optimum resolution for the device it's running on. And the next question is, why the artboard sizes look different than the actual resolution of the device? They look different because they are the 1x size and they are in DP. So all the things that you're seeing on the right, they are actually the 1x sizes of all the devices. If you multiply them with 3 or 4, you will get the actual resolution of the device. And although whatever I explained, all the mathematics that I've explained here, guys, is actually more centered towards Android, because the DP term is actually related to Android. But iOS also implemented the same thing in Swift, but it's on point. We have used 160 DP as a baseline thing, 160 PPI as a baseline thing in DP conversions. They use some different value for the constant, but the idea and the everything else is exactly the same, just that the value differs and the naming differs, but they also follow the same sort of system. And guys, I think that's it for today's video. I hope this video was informative for you, and I have skimmed the mathematics part in this video. But if you want me to explain you more on developer handoffs and more detailed video on the mathematics on how these things work, then let me know in the comments below and I'll make a video soon on it. And I think, yeah, that's it. And I'll see you in my next video, guys. Take care. Bye-bye.